Hello everybody. So here we're doing exercise 6.3 and we have three cases. Temperature of 300 Kelvin, a temperature of 3000 Kelvin, a temperature of 30,000 Kelvin, and a temperature of 300,000 Kelvin. So I start with the first one. We have to find the partition function for 300 Kelvin. Therefore, we have to say that Z is equal to the sum of e to the power of negative e to the power of s divided by kt. So we can start evaluating it. We know that our energy is equals to 2 electron volts for our stage, excited stage, and then ground state energy of 0. So the ground state energy will be the first value. Therefore, we're going to have e to the power of negative 0 divided by kt, not even going to write the rest because you already know, plus e, and now we actually use our energy values, which is negative 2 electron volts divided by kt, plus e to the power of, and then again we have our next value, which will be equals to, actually, we're just going to stop here because we have just two stages, two excited states. So the first one will be 1, and then we have e to the power of negative kt, e to the power of 2, and well, kt will be equals to 0.026 electron volts. So I have to put minus. So we have plus 3.9 times 10 to the power of negative 34. So we could just say that our function is just 1. It's approximately just 1. There's not much to add to this because negative 34 it's pretty much pointless to add. Then we can do the same thing for our second value for t is equals to 3000. So sum of e to the power of negative energy of s kt. Only two states, so we're going to only have two values, so e to the power of 0 plus e to the power of negative 2 electron volts divided by, so our k is 8.7, that's 10 to the power of negative 5, pretty much. So I'm going to say 8.7, 2 divided by 8.7 times 10 to the power of negative 5 times 3000. Okay, and then e to the power of negative of this. So we get 1 for the first one, of course, plus 4 times 7 times 10 to the power of negative 4, which equals 1.00047. For the third one, then we have the same thing. I'm not going to rewrite the first steps because it's going to be the same thing. So e to the power of 0 plus e to the power of, forgot, negative 2 electron volt divided by kt again. So we have again 1 plus, and then we have e to the power of negative 2 divided by 8.7 times the power of negative 5 times 30,000, which is equal to 0.46, which is equal to then, I'm rounding, of course, so 1.46. And then at 300,000, we have the same exact thing. Then we get 1 plus, we're just going to take our e to the power of negative 2 divided by 8.7 times 10 to the power of negative 5 times 300,000, which is equals to 0.93. So 1.93. One thing that we can notice actually is that At lower temperatures, we have lower z's, while at higher temperatures, we have higher z's. We're approaching a 2. So our value of z is always going to be in between 1 and 2. To be precise, as t approaches 0, then z approaches 2. Oh, sorry, one second. T approaches infinity, we have t approaching 2. Z approaching 2. Instead, as t approaches 0, we have z approaching 1. So these are the two things you need to remember, and we just checked them in our problem. I hope this is helpful. Let me know if you have any questions in the comments.